Hello. So I will talk about potential new applications of lasers, focus on causing de-excitation. Yeah, so we usually think about lasers as causing excitation. There are many examples of also using it for de-excitations. For example, the STED microscope, simulated emission depletion microscope, like here, that they use two lasers. So one laser excites this large dot, then the second laser causes de-excitation in this donut shape around. Finally, the dot is very small, so it allows to improve the resolution. Yes, so the second laser is indeed used to de-excite some target, some region, like here. So I'd like to talk about more potential applications and some new ones based on CPT symmetry. So thinking about some sending photons with some optical isolator, could we make the reverse version? So, for example, about some medical applications like computer tomography, potentially better version, radiotherapy, or two-way quantum computers, like here below. So we have a photonic chip. Usually, we would just um, inject photons inside and measure outside. However, let's also do the opposite from the other side. So from CPT perspective, we inject photons here, and the question is, could we control the flow of photons from both directions? Or in other words, could we couple resonators of lasers with photonic chip between them for better control of flow of photons? If true, then in theory they should be much more powerful. I will also briefly explain further. Okay, so let's start with this analogy between electromagnetism and hydrodynamics, which, if there is no viscosity for superfluid, are governed by very similar equations, like here in this. Okay, so need the same equations. So we have optical heating, but we can also do cooling. We have pushing, so we can also do pulling, also tweezers. So generally, the radiation pressure is a vector. So it can be positive toward the surface, but can be also negative outward a surface. So there is also negative pressure, but there should be also negative radiation pressure, which kind of allows us to pull a symmetric version. Okay, so let's think about these different ways for computation. So standard electronics, we have a chip, and the battery pumps kind of electrons inside this chip, and also actively pulls the photons with kind of with potential, electric potential, which acts as a kind of negative pressure. So actively pushes inside and pulls outside. So very similar is this microfluidic setting. So we have a pump which with positive pressure pumps liquid inside, and with negative pressure pulls outside, pulls here. So there are considered superfluid quantum computers. So having quantum computer based as microfluidic chip, to get this two-way quantum computer control from both directions, you would have to just connect it into a loop with pump. Yes, to have this two-way quantum computer, which is governed by this symmetric formulation, like in scattering matrix, that we have situation and the initial and final situation, and there is unitary evolution between them. So the question is, could we take it to electromagnetism? So the similarity suggests that we should be able to do it. So we could start thinking about microwave as the closest, but finally the most practical would be doing it on photons. So the question is, do we have something like pump for photons? And the ring laser seems to work like that. So ring laser, we enforce photons to travel, circulate in one direction. So if we look from CPT perspective, the circulation direction would be reversed. Yeah, so here we inject the photons here for state preparation, but from CPT perspective, we also inject them here from the CPT analog state preparation. So we both pushes with positive pressure photons from one direction and pulls with negative pressure from the other, or the opposite in the CPT perspective. Yeah, so the question is, could we create this kind of photonic computers controlled from both directions? If so, they would be much more powerful. So this is one of potential applications. Okay, so the basic rule here is the CPT symmetry. So physicists believe that the equations governing physics are CPT symmetric. So performing this symmetry on our universe, the equations should be the same. So it is required for Lorentz invariant quantum field theories with Hamiltonian. They have to be. This is Schwinger theorem. They have to be CPT symmetric. So if the CPT symmetry is violated, then we would have to recreate the fundamental physics. So it would be very bad. So most likely it's true. But so the question is, could we find some applications of CPT symmetry? And I don't know any. And the proposed ones are probably the first. So like two-way quantum computers and many others I will talk about. So if it will be violated, the proposed tests applications could show that it is violated, then we would have to, that would be also a problem. So we would have to change the physics. So the test, proposed test will be a kind of macroscopic test. So not on single particles like the previous. So there are many single particles microscopic tests. So and the proposed will be macroscopic for relatively large settings. So having CPT symmetry, so people ask what about entropy growth, which is obvious asymmetry. So like in this lake, if there are if the equation is symmetric, like the surface of this lake, if we throw a rock, we can break this symmetry. Yes, so symmetry in equations can be violated, broken in solutions. So it is not a problem. So we can ask what was this rock in our physics with entropy growth, and I think that the Big Bang could be thought this way because everything was localized, so entropy was low, and so it created the entropy of gradient of entropy we observe as second law of thermodynamics. And so now let's think about the most, I think, CPT symmetric process, the Rabi cycle. So we have two resonators. So we have laser, we have some target, which are some tiny resonators as atoms, for example, and they periodically exchange energy with the two equations. So there is this absorption equation in which we increase the number of excited atoms and simulated emission in which the laser causes decrease of the number of excited atoms. Yes, so the laser periodically pushes photons and pulls photons. And from CPT perspective, this is nearly the same. Yes, CPT perspective, we just replace these two equations and switch this simulated emission with absorption. Yes, so this is very symmetric equation. And it has both. Laser causes both excitation and de-excitation. And so the question is, could we separate them and extract only this laser causes de-excitation? Here we are more interested for the application I will talk about. And optical isolator seems this kind of basic tool, which allows to only one of this type of photons. Okay, so let's go further to this Rabi cycle, like here. So there are these mechanical analogs like the couplet resonators, like the couplet pendula. Yeah, so we have two pendula couplet here, and there are periodically exchanging energy. Yeah, so there is left and right. So like in this Rabi, there is exchange of photons of energy going in both directions. So thinking about this laser, so we have some asymmetry. This is a strong source of energy, and these are tiny resonators. So maybe we could think about a fan, which can also excite the excited resonator. Yeah. So if we push with fan, we can excite, but pulling with fan, we should be also kind of extract energy from excited pendulum. Yeah. So another more hydrodynamical view could be like here that we have a standing wave in the tank, and there is some semi-transparent wall, and this standing wave creates also waves outside, which, for example, makes this left-right behavior of this particle. So with positive negative pressure. Yeah. So this this resonator acts with cyclically with the positive negative pressure. So it's kind of similar to Rabi cycle. Okay, so the problem is that lasers usually have built-in optical isolator, which forbids one direction of this photon. So why naively we would like to have this resonator like here direct realization. When looking in the literature, I have found two types which I think go around this problem that usually lasers have optical isolator. So one approach is like here that there is additional resonator. So let's here look at the simplified situation that we have a laser with optical isolator which pumps the resonator, and the proper Rabi is between this resonator and the tiny resonators of atoms. Yeah, so here is the main Rabi, while laser only pumps this resonator. And the second approach I have found is this Mach-Zehnder-like. We can also think that looking from CPT perspective on this setting, we kind of reverse the photon trajectory. So there are ways to go around this problem that there is optical isolator, but maybe we can instead of going around, maybe we could make this simpler direct realization by just removing optical isolators. This is, I think, an interesting question and practical because quantum computers often use the Rabi cycle. Okay, so now let's go to synchrotron radiation, kind of the main actor here. So we have a charge like electron usually traveling on circle, but in practice on this spiral because it radiates energy as photons with this formula. So to avoid this spiral, there is regularly used acceleration. Like here, so we have lines for acceleration, and then there is this angle for synchrotron radiation. So the question is, what about CPT symmetry in here? Yeah, so in CPT perspective, if you reverse time, the spiral would be outward. So it kind of makes no sense. So let's think about it. So in standard synchrotron radiation, we just emit photon but not absorb. But in theory, this is very similar to antenna. Antenna can both emit photons and absorb photons. So in theory, I will provide more arguments, but in theory, it should also be able to absorb photons if only there is source for these photons. Usually there is no. But let's think about synchrotron radiation close to, let's say, cosmic microwave background radiation. So there is some noise everywhere, electromagnetic, and if having synchrotron around this noise, shouldn't these electrons both emit and absorb these photons? So maybe we could get slower this losing of energy because it would also both emit photons and absorb photons. Yeah. So it's worth to adding into consideration that also absorption of photons into the this accelerating charge. So finally, here is the T symmetry of this picture. So after CPT there should be similar equation, but this electromagnetic already T symmetry should be sufficient. So what's happening? So here we have electrons circulating, and they produce photons, and which excite atoms in this target. Yeah. So but there is also distributed emission. So it also causes the excitation and further here. But to be in agreement with CPT symmetry, we need also the symmetric parts. So also here we should have this created photons, the excitation, and so on. So to showing this in one picture, we have both. So you should both push these photons here. So we have both symmetric emission in this direction, so kind of positive radiation pressure and knocking out the photons of excited targets here. But also we should have this symmetric to this picture photons, which kind of pull with negative radiation pressure. So we should have both. So I will show more arguments. So one more, this hydrodynamical analog, which mathematically should be very similar. That if we have this marine propeller, it creates these waves which carry like photons. They are very similar to photons, carrying all energy, momentum, and angular momentum. And can be both. We can reverse the rotation and we reverse the pressure. So this way, if you think that there is a resonator here, so it should be able, like this fan mentioned previously, should be able to both excite this resonator and cause it de-excitation. It should be able also to intuitively to take energy, to pull energy from this resonator. Yes, it should both work in both directions to answer the problem. What about the CPT symmetry here? So there are some. I found one article considering the CPT symmetry and synchrotron radiation. So with this picture, that indeed there is not only emission of photons, but there should be also absorption of photons. Also, there are these basic Feynman diagrams like here that can be photons can be emitted and absorbed. And finally, so there is also this Compton scattering when electron both absorbs and emits photons. So usually there is some difference of energy, uh, inverse or one is larger or smaller depending if inverse or the original one. But then it's possible that it should be CPT symmetry says that electrons should both emit and absorb. Yeah, so you have antenna, it can both send and receive. So let's think about this CPT symmetry perspective of synchrotron radiation. So we have just accelerating charge usually on the circle if in constant magnetic field, for example. So there are created photons, but looking at CPT perspective for CPT, the equation should be the same, and this is still charge on a circle, accelerating charge, so it should still create photons in CPT perspective. But in our time perspective, these CPT photons, in fact, go here. So they cause not excite target, but cause de-excitation of the target. Yes, so the standard photons act with this equation, try to excite the target, while these CPT photons should act with this equation, should cause de-excitation of target. Yes, kind of pulling photons. So CPT symmetry, however, to make it happen, we need the target is excited. So usually this is this missing condition like here that we have the circle because there is only it's easy to produce photons, but it is difficult to have a source for these photons. Yeah, so there is asymmetry, not in equation but in the solution we live in. That these photons will likely be absorbed in some future somewhere, but to absorb the photons, they would have to be emitted in our past. So there is asymmetry in solution, not the equations. Yeah, so also we can think about different conditions. So, for example, as mentioned, if we would work with the microwave background radiation, so there should be both emission and absorption here. Or if you think about future of the universe, there is this thermal death where everything is synchronized. So maybe there will be different behavior here. Okay, so finally we have these two equations. So one from the Rabi and the second from the Rabi, let's say. And here is the last slide about this hydrodynamical analog and cyclotron radiation. So thinking about this hydrodynamical analog, if you have a fluid and we push something in this fluid, then we create positive pressure, but we also create negative pressure. Yeah, so this should be symmetric. And in CPT perspective, they are switched. Yeah, so this is CPT symmetry view. They are switched. This marine propeller rotates in the opposite direction. So instead of positive pressure, it creates negative pressure. So instead of exciting a resonator, it should cause de-excitation of resonator. Yeah, so and this circular antenna is quite of similar, but so I think it could be improved by changing shape from planar to let's say ellipsoid shape. Maybe we could have better control like this marine propeller antenna like. So again, having this accelerating charge, it should produce photons, and in CPT perspective, it is still accelerating charge, so it still should still produce photons, but these photons for us cause de-excitation instead of excitation. And they require that target was already was initially excited. So this is the difficult condition why we usually don't see this effect because it is not satisfied. But we could try to satisfy it artificially, and so maybe this is some the first idea how to use it. So as a camera. So standard camera is focused on being excited, yes, on this part that it sends photons and it excites our atoms in our detector. So maybe let's think about CPT analog of this picture. So now you would need the camera which is excited, and with stimulated emission, this accelerating charge should cause de-excitation. Yeah? So these photons cause excitation in our negative time, and for our time perspective, they should cause de-excitation. So these photons should cause de-excitation in our target. So you'd need a detector which is constantly pumped, and we monitor its population. Yeah, so in both we monitor population. So this way we should be able to find the strength of this kind of effect. So in stars there could be, for example, I think synchrotron radiation should it's hard to avoid it. So this way you should be able to construct a camera which can see synchrotron radiation, but probably not thermal radiation. So I think it would be very interesting to see what does such backward camera which is focused on this stimulated emission from the target, what can it observe? So probably synchrotron radiation, but probably cosmos will hide many other very interesting objects it will be able to see. Yes, and from pressure perspective, so again, so this one is focused on the positive pressure, radiation pressure, and this one is focused on the negative radiation pressure. Yes, and we have to remember that to make it work, it has to hit excite the resonator, like atom, like pendulum excite. Yeah, so this is crucial that this kind of coupling with the resonator, like atom or something else. Okay, so let's think about another application similar to this backward camera. So let's think about CT scanner, computer tomography scanner. Standard one makes 3D maps of absorption coefficient. So we have a source of photons, let's say laser, so this ring laser that we have circulation in only one direction. And here is the detector, which is cooled, and we monitor populations of the detector. And on the between there is let's say a human body, and it subtracts kind of the number of ground state atoms on the go. Yeah, so it subtracts the absorption coefficient uh, for this life path with kind of positive radiation pressure. Yeah, so let's perform CPT symmetry picture of this situation. So we have still a ring laser, but we reverse the circulation. So now it should, instead of it pushes here, so it should pull here. So now it should cause de-excitation in the target. So here we have to use pump detector. That's a difficult part that we need a detector which is constantly pumped. And we monitor its population somehow, so it's not trivial, but I think it's doable. I have a few ideas how to do it practically. And then there is this target, and now it subtracts not the ground state, but the excited atoms. So it is why it's better, because the number of excited atoms usually much smaller than of ground state atoms. So it should have much better transparency. So while standard light goes maybe like 1 centimeter into a body, these photons should in theory be blocked not by ground state, which stops the standard photons, but by excited state, so kind of negative radiation pressure photons. So it like if it like 10 times 10, the number that is 10 times smaller, then it should be easily go through the entire body, human body. So that there is a chance to measure emission coefficient on the go. So having it for many planes. In computer tomography, we could make this radon transform or multiple angles, and we get for example, three-dimensional maps of emission coefficient inside a body. So, for example, turns out there are many molecules which are already excited in our body. So there are called autoluminescent molecules, which are excited by the chemistry, by biochemistry of our of the life. So for example, an NADH. So this is crucial for this Krebs cycle. So to make So it's for metabolism to make energy. So especially this one. So in theory, we should be able with this kind of this CT scanner of emission coefficient, we should be able to make 3D maps of various these molecules, autoluminescent molecules. So so kind of Röntgen like, but without ionizing radiation, so much safer. And multispectral. We have multiple frequencies, so we should be not just black and white, grayscale like standard computer tomography, but multiple colors which correspond to different molecules, which we should be able to for much better distinguish various tissues. Okay, so but the question is how to make. So one question is how to build this backward camera, focus on the stimulated emission from the target. The second, how to build this source of negative radiation pressure. Yes, also CPT analog of standard source of photons. So there are many possibilities, theoretical possibilities. So the simplest might be just reversing optical isolator, but I think it's too simple. So more sophisticated is this ring laser that we have enforced circulation of photons in one direction because of this optical isolator, which allows only photons in one direction. So standard ring laser would leave the photons going here, so would excite this target with this equation. But looking in CPT perspective, the photon circulation will be reversed, so it should excite this target with this equation. But this was in CPT perspective, so in our perspective, it should act in the second equation, the stimulated emission equation. Yeah, so like again, like synchrotron, it should both cause the excitation here and cause the excitation here, acting with the two equations. So push with positive pressure here, radiation pressure, and pull with negative radiation pressure from here. Another approach could be these free electron lasers, generalized synchrotron radiation. So we have again we have charged particle going one direction, producing photons and causing excitation of this target with this equation. In CPT perspective, it goes in the opposite direction, changes and excite this target. So in our perspective, it causes de-excitation with this equation. Or just let's say synchrotron like here. So as mentioned, it should both cause excitation here and stimulated emission here, but also in CPT perspective, they are switched. So it should also cause, so yes, we switch the two. So it should also kind of pull photons here and push photons here. Yeah. So CPT symmetry requires this also the second causality, which I think you have many applications. So another application related to this medical one is just causing the excitation. Yeah, pulling photons in given direction. So there could be many applications. For example, some chemistry to pull photons to speed up the excitation given frequency, like the STED microscopy mentioned at the beginning. So the problem with the STED microscopy is that it bombards with photons. But maybe if you could pull photons with negative radiation pressure, it would be better as without this photo bleaching. So they are complaining about photo bleaching that is bombarding with photons is destroy the sample. So maybe just being able having this negative radiation pressure, we should do it instead like without photo bleaching. Then then the transparency should be very interesting. That why standard photons are blocked by N1, but the ground state atoms, these CPT photons, should be kind of negative radiation pressure should be blocked by N2, by excited atoms on the go. And usually there is much lower number, so there should be much better transparency. So it can be chemistry, some photolithography, some reverse photolithography. Is that we have a surface, we excite it, and with laser we try to pull photons to de-excite it very selectively. Yes, for some reverse photolithography. Maybe some nuclear, I will mention in a moment. Maybe some neuro, if there is better transparency, maybe we could affect processes in our brain. Things might be dangerous. Medical finally. So here is this first medical possible application. So I've mentioned that this NADH is continuously excited by the life itself, and it's required for the metabolism of the cell. So if we could cause the excitation, yes. So there it can be the excited with producing energy, producing photons. So if we could pull these photons, so what should have much better transparency, we should be able to starve the tissue because we have no energy as the metabolism would be damaged. So maybe we could intersect multiple such these negative radiation pressure beams in the point to speed up degradation of an HDH like 10 times, and for intermediate tissues like some percentage of some small percentage, maybe also circulating these to cover the intermediate paths over a large volume. So this way we should have large damage as starving for the target tissue and very small, hopefully without any side effects for the intermediate tissues. Yeah, so to just very precisely starve deep tissue. Okay, so maybe also some nuclear potential applications, but so for synchrotron, they are able to reach keV, MEV scale energy, so photons. So maybe we could make like kind of STED-like causing the excitation, but for nuclear physics. So think about Solaris, the synchrotron here. So it could reach, let's say, 20 keV photons. So here are the down to 20 something keV gammas released in nuclear decays. So let's think about, for example, this erbium 169. So it decays in 9 days to here, and then in nanoseconds, in 4 nanoseconds or 4 nanoseconds to the ground state. So to speed up it, so probably we could speed it up. Yeah. So it's also considered mainly for isomeric transitions, like induced gamma emission, for example, for considered gamma ray laser, but it's very far from being practical. But maybe you could speed up just this transition. So, but it's not very practical. So, and after 9 days, we would like to speed up 4 nanoseconds process. However, maybe you think about this camera. So this camera, as mentioned, requires this backward camera requires continuously pumped target. So maybe we could use, let's say, this erbium 169 as this continuously pumped target. Yeah. So we put this erbium here, and and put some target on the go, and monitor and try to make this kind of CT tomography of this target. So potentially it could be used, I think, for this backward camera. Yeah. Okay, so another application, another potential realization is very similar in literature, is so-called amplified spontaneous emission, where here we have excited target, erbium in fiber optics, very popular, and now the laser here literally pulls photons here, so causes the excitation toward left, and then it goes to the circulator and goes down. So this is potential one of applications, realization. So but yeah, maybe but it needs more work. Okay, so now going to this backward camera. So we have something what pulls photons. Yeah, so hopefully with negative radiation pressure. So the question is, we would like to measure how strongly the target pulls photons from us with negative radiation pressure, with simulated emission cost. So how to do it? So one could be monitoring of this population. So for example, we have for two-dimensional camera, you would have a pumped surface, maybe made of this erbium 169 for gammas. So we have this pumped this display, and now we could monitor its population. So this is one direction. Another direction could be that we put, let's say, semi-transparent mirror here, and here put the main CCD CMOS matrix camera. So hopefully we should monitor how much this target pulls photons from our excited target. Yes, for our this active sensor, you can say. So this is one more practical, hopefully, realization of this backward camera focus on this negative radiation pressure from the target. Another potential application could be this backward lighted camera. So now you would like to cause the excitation of the target, like here, to make it produce more photons in given frequency toward our camera. Yeah, so like standard lighted camera, but instead of shining on the target, we would like to directly pull the photons in given frequency. Yeah, so for example, thermal photons, but maybe also for attacks of, let's say, BB84, the cryptographic protocol where it's assumed that the laser of the sender sends single photons, but the attacker could make it produce more photons in the same conditions and try to steal some of the photons and get the message. So it could be used also for attacks of quantum cryptographic protocols. It's trying to pull the photons from the laser used by the sender. Okay, so some maybe related articles that there was observed negative delays. Here is one such 2003 article which says that the delay between the before and after this cell can get to negative one of the impulse. And here is the recent one by Steinberg group saying that with very simple setting, that just some rubidium and single photons and probe, then they got some. Here is the impulse, and they get a response both before and after the impulse. So mainly for the post selection for the photons, but also without the post selection. So I think maybe this CPT symmetry might be the answer. Because the target, the photons, yeah, so maybe here is the answer in the CPT symmetry, but so it needs more discussion. Okay, so now let's think about this. So there is this textbook view that while there is spontaneous emission in random direction of excited atom, there is absorption like here. The question is, what is stimulated emission? So standard view is like here, that the photons causes creation of kind of knocks out more photons. But the CPT symmetry, Rabi cycle suggests that maybe this is the opposite, that there is pulling. So I think there are separate and both are true. And having the second one, we can also explain this one. So let's think about this pulling of photons. So imagine that here we act with this negative pressure. So it cannot pull photons from here because it was ground state, but it can pull photons from here. So it pulls photons from here, and some of them are absorbed by the target. By target. Yeah. So CPT perspective of this picture is this textbook view. So I think this is a consequence of CPT symmetry. So maybe, but generally, because we should think about them as kind of two types of pressure. One stimulates emission outward, and second stimulates emission toward us, kind of positive and negative radiation pressure. Okay, so let's see a few slides about these two-way quantum computers, potential and much more powerful than standard one. So in standard one-way quantum computer, like here, we start with state preparation, then we have unitary evolution, then we measure everything, so a part of them. In two-way quantum computers, we assume that if you can prepare, then we should have also this CPT symmetric view. So we have post-paration. So preparation and post-paration. So do the same. So do the process which in CPT perspective is the original state preparation process. Yes. So doing so, we should be able to get this CPT analog of state preparation. So to use this kind of formulation as in scattering matrix. So for example, in silicon quantum dots, so we have these dots, and we use impulse to tunnel the electrons into the dots. So the question is how to reverse this process. We just apply the opposite impulse at the end, and from perspective of CPT symmetry, we have performed the original state preparation process. Yeah, so it sounds trivial to reverse the state preparation process. So this is one example that having a process allowing for state preparation, it is relatively easy to get a process which in CPT perspective is the state preparation process. So we should have both state preparation and state post-preparation. Okay, so we have a team for the Google X Prize competition. So there are some articles. So I've mentioned about this situation that we have laser resonators and photonic chip between them. So we have coupled resonators, with some control, some sophisticated control between them. So intuitively, it should allow for some better power, computational power. So there are many arguments it should work. I haven't met for these nearly 2 years any counter argument. So in theory it should work, but it needs more help with experimental people. So this is we search for collaboration. So I have mentioned this silicon quantum dots, one approach. Another approach could be that in many approaches we use very low temperature for state preparation. Yeah, so if there is a temperature like 30 millikelvin or lower for superconductor quantum computers, then we can assume that nearly all qubits are in the ground state, basically, yes, because of the Boltzmann distribution. And so because of low temperature, so we prepare state by lowering temperature. But from CPT perspective, the temperature is the same. So such lowering temperature should act both as this preparation and post-paration. Yes, so we should be able to also use it after. So here is some example of two-way quantum computer, so that we have state preparation, standard one, but then we just don't do measurement. Yeah, so without measurement, which is quite invasive process, so which can exchange energy. So if we don't do it, then from CPT perspective, we have just state preparation. Yeah, so we can think about it as just losing energy to this reservoir, but from CPT perspective, we have just started with this ground state and go into this unitary evolution. So why it shouldn't work? So I think this is the most promising approach. Yeah, so that need help. And okay, so assuming that we can have this post-paration, now I will try to convince you that we, in theory, should be able to attack the NP problems. So for NP problems, we have some verifier which can say that if given input is correct or not, in reasonable, in polynomial time. But the problem is that there are exponential numbers. There's a very large number of possible inputs. But we can easily check if given input is right, but there are extremely large number of them. So for example, this is a problem. We have this verifier as just asking if one of this this alternative, which can include negation, is true, and all the alternatives have to be true. So the question is, so verifier is very simple. Yes, that just checking if all the alternatives are true. But the number of inputs, what values we really give to the variables is exponential. So this is, and if being able to solve this TSAT problem, in theory, we should be able to solve in polynomial time all the remaining NP problems. So it being so, for example, you could break ciphers. So this could be dangerous. So for example, for cipher breaking, so not just RSA, but in all ciphers. So I don't know how to avoid it. So for example, that we have in cipher also symmetric. We have a decoder which has some prefix and the key and decodes into the decrypted prefix, this beginning of this file. So for the wrong key, it should be a noise, but for the right key, it should be the entropy should be reduced. Yeah, so the verifier could just check if the coding some initial part we get lowered entropy or not. And so this way it is becoming an NP problems. The problem is, so having solver we could try to break cipher. So it could be dangerous. So this is the negative side, but there are also many positive sides that, like, let's say, the drug design, generally global optimization. That we have a complicated function like this, and we would like to find the best solution or the best algorithm solving in infinite time given problem. So having a NP solver, there will be many positive applications, but we have to also remember and the cryptography part. So also, two-way quantum computers, I will show in a moment that in theory allows to attack NP problems and also allow for better stability, better error correction. Okay, so how to solve TSAT, assuming that we have this post-paration. So we can start with state preparation, then Hadamard gates. So now we have prepared superposition, quantum superposition of all the inputs, exponential number. Then we would like to calculate these alternatives. So here is this alternative with some knots. So we calculate this verifier, and now usually you would measure here, but in two-way quantum computer, in theory, we can enforce it to values exactly like the preparation enforces initial value. So now we'd like to enforce it to true. So all the alternatives have to be satisfied. So this should restrict the ensemble to only satisfying our NP problems. So just measuring it, we should solve our NP problem. Yeah, so it is very similar to Shor. So Shor is very similar at the beginning. Also prepares the exponential number with Hadamard's. Then it makes them calculate some classical function here, but then it measures. So this measurement restricts in Shor to periodic superpositions, and so Fourier transform allows to get this period what gives hints to the problem. So here instead of measurement, here we would like to enforce it to one. So this post-paration. So the question is, can we do it? GPT symmetry suggests that we should be able to do it. Okay, so here is the final slide. So summary. So the question is, so generally the basic question is, how to generate and measure this negative radiation pressure? Yeah, so like standard laser creates positive radiation pressure. Can you get negative, which not pushes photons but pulls photons? Right? So like here for the synchrotron, we should get both the positive radiation pressure, which also causes the stimulated emission here, but should also has negative radiation pressure, which is the opposite, and in CP perspective there are opposite reversed. Yeah, so now. So because there is this positive pressure here, there should be negative pressure here. Or in this ring laser, we have circulation of photons which would go here, and CPT perspective, they go here, yeah, because we change the photon circulation. So the question is how to do it practically. So I don't know. So maybe ring laser or synchrotron radiation should allow to do it. Hopefully, at least CPT symmetry says it should allow. They should allow for that. If they don't, then maybe we could show that CPT symmetry is violated. What would be also extremely interesting and requiring to change physics. So having this source of negative radiation pressure, which is one of these two approaches, so some applications could be direct Rabi without any tricks as mentioned, like by just removing optical isolator maybe, or instead without photo bleaching by reversing optical isolator, so using negative radiation pressure, so using this pulling instead of pushing photons in STED microscope. Then causing deexcitation. So like STED, but maybe by pulling without bombarding with photons. So for example, radiotherapy to starve tissue deeply in body, thanks to better transparency, maybe some nuclear transitions. Then is backward camera. So how to measure this negative radiation pressure? So we need camera of excited target. So maybe astronomy, maybe on this computer tomography better. So there are, I think there will be many applications with backward camera, but it is not so simple to construct. Backward light camera, so which tries to actively pull photons from the target to get to our camera. So also to attacks for cryptographic protocols. Emission CT as combined backward camera with negative radiation source. And finally, two-way quantum computers. So each theory should be possible, let's say with positive radiation pressure and negative radiation pressure to control the flow. And if so, they are much more powerful than the standard quantum computers. Okay, thank you for the attention.